Imagine standing still, gazing at the stars, and then suddenly accelerating to speeds unimaginable, approaching the cosmic speed limit of light itself. What would the universe look like? How would space and time behave around you? The answers are far more bizarre and fascinating than anything you encounter in everyday life. Buckle up as we embark on a mind-bending journey through the physics of near-light speed travel, gravitational time dilation, and the enigmatic nature of time itself. This exploration will unravel the mysteries of the universe, from the relativistic Doppler effect to quantum experiments that challenge our understanding of reality. Prepare to see the cosmos in a way you've never imagined, and stick with us to the end for a surprising revelation about light and time. Picture yourself accelerating through space, not just fast, but at velocities so immense they rival the speed of light, 299,792,458 meters per second, the ultimate speed limit of the universe. According to Einstein's theory of special relativity, nothing with mass can ever quite reach this speed. The energy required to accelerate an object with mass, like a spaceship or even a single particle, grows exponentially as you get closer to light speed, demanding infinite energy to cross that final threshold. Only massless particles like photons can travel at this cosmic constant, yet scientists have observed particles such as those in particle accelerators reaching speeds up to 99.9999% of light speed. While we humans may never experience such velocities, let's dive into a thought experiment to explore what would happen if we could. Imagine you're in a virtual simulation, much like the one developed by MIT called A Slower Speed of Light. In this game, you start walking normally, but as you collect orbs, the speed of light itself slows down, simulating what it would feel like to move at relativistic speeds. At first, the world looks familiar. Trees, buildings, and skies appear as they always do, but as you speed up, or rather as the speed of light slows to mimic your rapid motion, reality begins to warp in extraordinary ways. One of the first changes you'd notice is a dramatic shift in colors. As you approach light speed, the light reaching your eyes undergoes the relativistic Doppler effect. Normally, the colors we see depend on the wavelength of light. Red for longer wavelengths, violet for shorter ones, with infrared and ultraviolet lying just beyond our visible range. But at near light speeds, the wavelengths of light shift dramatically. Infrared light, normally invisible as heat, stretches into the visible spectrum, glowing in hues of red. Ultraviolet light, once beyond your perception, shifts into blues and violets. Suddenly, objects that were invisible, glowing heat sources or fluorescent materials, become vividly apparent. The faster you go, the broader your visible spectrum becomes, transforming the universe into a psychedelic canvas of colors never seen in everyday life. This isn't just a visual spectacle, it's a consequence of your motion through a stream of photons, the particles of light. As you race forward, you collide with more photons head-on, making everything in front of you appear brighter, a phenomenon called the searchlight effect. Glance backward and the opposite happens. Fewer photons reach your eyes, cloaking the rear in darkness. The universe itself seems to bend to your speed, with light behaving in ways that defy intuition. As you continue your relativistic journey, another strange effect takes hold. Time itself begins to behave differently. According to special relativity, the speed of light is an unbreakable constant, but space and time are malleable, warping to preserve this cosmic rule. This leads to a phenomenon known as time dilation, where time slows down for an object moving at high speeds relative to a stationary observer. Imagine you're traveling in a spaceship at 99.99% the speed of light. From your perspective, everything feels normal. Your clock ticks as usual, your heartbeat remains steady, but to an observer back on Earth, your time appears to crawl. If you travel for 1 year from your perspective, a stationary observer might see 10 years pass on Earth. This isn't science fiction, it's been proven. In 1971, scientists conducted the Haffele-Keating experiment, flying atomic clocks on airplanes around the world. When compared to stationary clocks, the flown clocks ticked slightly slower, confirming time dilation. Even satellites in orbit, like those powering GPS, require time adjustments to account for their high speeds, which cause their clocks to lag by microseconds each day. In our simulation, as the speed of light slows, it feels like you're moving faster, even though your walking speed remains constant. This is because your time is slowing relative to the world around you, making distances seem shorter. You cover vast expanses in what feels like moments, but to an outside observer, years might have passed. If you could somehow reach the speed of light, an impossibility for anything with mass, time would stop entirely from your perspective. Photons traveling at light speed experience no passage of time, existing in a timeless state as they zip across the cosmos. As you hurtle forward, another bizarre effect distorts your perception: the aberration of light. Light takes time to reach your eyes, so you're always seeing objects as they were in the past, even if only by a fraction of a second. At near light speeds, this delay becomes significant. Objects no longer appear where they actually are, creating a disorienting effect. In the MIT simulation, navigating becomes challenging as you crash into walls or miss objects, not because of poor reflexes, but because the light reaching you is lagging, showing objects in positions they've already left. This aberration also expands your field of view. As you move faster, light from objects around you, behind, to the sides, and even slightly ahead, bends toward your line of sight, giving the impression that the universe is compressing in front of you. It's as if you're peering through a fisheye lens, with your surroundings stretching and warping. This is a consequence of the Lorentz transformation, a mathematical framework in special relativity that describes how space and time coordinates change for observers moving relative to each other. The faster you go, the more pronounced this warping becomes, transforming the universe into a surreal, tunnel-like vista. Despite these fascinating effects, traveling at the speed of light remains a physical impossibility for anything with mass. The energy barrier is insurmountable, and even approaching light speed introduces practical challenges. If you were in a spaceship, the outside world would appear drastically warped, colors shifting, time stretching, and your field of view expanding into a distorted panorama. Yet from your perspective, everything inside your ship would seem normal, a testament to the relativity of experience. If you could somehow travel to a star 40 light years away at light speed, you'd arrive instantaneously from your perspective, but 40 years would pass on Earth. Upon your return, you might find Earth transformed. Decades, centuries, or even millennia could have elapsed depending on your journey's distance. This is the essence of the twin paradox, a thought experiment where one twin travels near light speed and returns to find the other age significantly more. The universe, as you know it, would never be the same. Now, let's shift gears and explore another mind-bending aspect of relativity: gravitational time dilation. According to Einstein's general relativity, time doesn't just slow down with speed. It's also influenced by gravity. The stronger the gravitational field, the slower time flows. This phenomenon, while subtle in everyday life, has profound implications near massive objects like planets, stars, or black holes. Consider Mercury, the planet closest to the Sun. A day on Mercury lasts about 58 Earth days, 15 hours, and 30 minutes, as measured by its rotation relative to the Sun's orbit. But time itself behaves differently there, due to the Sun's immense gravitational pull. To understand this, let's use Einstein's equation for gravitational time dilation. Ta0 equals TF times the square root of 1 minus 2 gm divided by RC squared. Here, T0 is the time experienced in a gravitational field. T is the time in a gravity-free reference frame. G is the gravitational constant. E is the mass of the gravitating object, like the Sun. ER is the distance from its center, and C is the speed of light, approximately 299,792,458 meters per second. Let's apply this to Earth. If 60 seconds pass in a hypothetical gravity-free environment, how much time passes on Earth, influenced by its own gravity? Plugging in Earth's mass, 5.972 times 10 to the 24th kilograms, and the distance from its center, about 6,371 kilometers at the surface. We find that 60 seconds in a gravity-free frame corresponds to 59.999996 seconds on Earth. This means you'd need roughly 6 billion seconds, about 190 years, for a 4-second difference to accumulate. Over a human lifetime, you'd gain a mere 2 seconds compared to a gravity-free existence. Not exactly life-changing. Now, let's consider the Sun's gravity, which affects Earth more significantly due to its massive size. 1.989 times 10 to the power of 30 kilograms. Using the same equation with Earth's average distance from the Sun, 149.6 million kilometers. 60 seconds in a gravity-free frame becomes 59.99994 seconds on Earth. This translates to a 1-second difference every 3 years, or about 24 seconds over an 80-year lifespan. Still, it's a small effect. On Mercury, closer to the Sun at an average distance of 57.9 million kilometers, the effect effect is slightly more pronounced. For every 60 seconds in a gravity-free frame, 59.9999 seconds pass on Mercury. You'd need 60 million seconds, about 1.9 years, for a 1 second difference, equating to roughly 38 seconds over a lifetime, 14 seconds more than on Earth. From your perspective on Mercury, time feels normal, but an observer on Earth would see you aging slightly slower. If you pointed a telescope at Earth, you'd witness 14 extra seconds of its history over your lifetime. While Mercury's proximity to the Sun does slow time, the effect is minimal. To experience significant time dilation, you'd need a far more massive object, like a supermassive black hole at the center of a galaxy with a mass millions or billions of times that of the Sun. Near such a behemoth, time could slow to a crawl, spend an hour near its event horizon, and centuries might pass on Earth, cross the event horizon, and time as we know it ceases to apply. Our equations break down, leaving us in the realm of speculation. Time is a concept we take for granted, yet it's one of the universe's greatest mysteries. As Mark Twain quipped, time keeps everything from happening all at once, separating yesterday from today and today from tomorrow. We experience time at a steady rate, 1 second per second, moving inexorably toward the future. But what is time, really? Can we touch it, see it, or alter its flow? Einstein's theories suggest time is more than a ticking clock. It's a dimension intertwined with space in a unified space-time. To grasp this, let's start with the familiar 3 dimensions of space: height, width, and depth. These dimensions allow movement in any direction: left, right, up, down, forward, backward, at 90-degree angles to each other. A 2D world, like a flat sheet, restricts movement to 2 directions, say left, right, and forward, backward. A 1D world is a single line, where existence is confined to 1 direction, like beads sliding on a string. Now imagine adding a 4th dimension in 3-dimensional space. Drawing a line perpendicular to all 3 existing dimensions is impossible. Yet Einstein proposed that time is this 4th dimension, a direction we're all moving through, albeit one we can't see or navigate freely. To visualize this, let's compress 3D space into a 2D plane labeled space, and use the 3rd axis for time. In this model, you're a 2-dimensional figure moving upward through time at a constant rate, from past to future. Your motion through time is like a sailboat carried by a steady wind. You can't slow or stop it, but what happens if you move through space? According to relativity, the faster you move through space, the slower you move through time. This is where vectors come in. Imagine your motion as a vector, a fixed length arrow representing your total speed through space-time. If you're stationary in space, your vector points entirely toward the future, maximizing your speed through time. But if you move through space, your vector tilts, diverting some of your motion from time to space. The faster you move in space, the less you move through time. At the speed of light, your vector would lie flat, moving entirely through space with no progress through time. Hence, photons experience no time. This model explains why objects at high speeds appear flattened to outside observers, a phenomenon called Lorentz contraction. As you tilt your vector towards space, your shape in space-time compresses in the direction of travel. From your perspective, you feel normal, but the universe around you warps. Objects stretch at the edges of your vision, and your destination seems farther away. This flattening and stretching are precisely what we observe in relativistic scenarios, aligning perfectly with Einstein's predictions. But why can't we see time as a dimension? Our model suggests we're flat in the time dimension, like pancakes with no thickness in the 4th direction. We don't extend into the past or future, limiting our perception to the present. This raises profound questions. What force propels us through time? Why can't we move backward? While our model allows for a vector pointing downward, backward in time, reality seems to forbid it. These mysteries deepen our understanding of time as a dimension, revealing the universe's complex interwoven fabric. Light, the universe's speedster, never ceases to surprise. For centuries, scientists debated whether light is a particle or a wave, as it exhibits properties of both. It travels at a constant 299,792,458 meters per second in a vacuum, regardless of your frame of reference, a cornerstone of relativity. Yet, light can slow down in materials like water, 225 million meters per second, or glass, 200 million meters per second due to interactions with electrons, which create secondary waves that interfere with the original light, reducing its effective speed. In extreme cases, scientists have slowed light to a crawl, 61 kilometers per hour in a supercooled sodium cloud, or even stopped it entirely, only to release it later. But light's strangest behavior emerges in experiments like the double slit experiment, which reveals its dual nature. When light passes through two slits, it creates an interference pattern, behaving like a wave. But observe which slit it passes through, and it acts like a particle, hitting a single point. In 2023, researchers at Imperial College London took this experiment to a new level by creating time slits. Using indium tin oxide, a material that can switch from transparent to reflective, they fired laser pulses and briefly made the material reflective, creating temporal slits, moments when light was reflected rather than transmitted. When two laser pulses passed through these time slits in quick succession, an interference pattern emerged, not in space, but in the light's frequency. Certain frequencies faded, mirroring the intensity patterns of the spatial double slit experiment. To understand this, imagine a 4D graph with space on the x-axis and time on the y-axis. A photon travels from an emitter, hits a time slit, reflects, and reaches a receiver. A second photon follows a similar path at a later time. Normally, these paths wouldn't interact, but the interference pattern suggests the photons are testing multiple paths through time, including paths that seem to move slower or faster than light speed, even backward in time. This doesn't mean light literally travels backward. Rather, it explores alternative paths, like lightning probing for the fastest route. The interference pattern implies light is sampling paths that cross both time slits, affecting its frequency. This challenges our understanding of causality, suggesting light operates outside the strict forward march of time, at least on a quantum level. If light's temporal antics weren't strange enough, quantum mechanics takes things further with experiments suggesting information might defy time's arrow. In the macroscopic world, time flows forward, and sending information backward would create paradoxes, like warning your past self about a bad decision. Yet, quantum experiments like the Bell test and the delayed choice quantum eraser hint at a reality where time is more fluid. The Bell test, inspired by physicist John Stuart Bell, probes quantum entanglement, where two particles linked by a shared quantum state instantly reflect each other's properties, no matter the distance. For example, if two particles are entangled with zero total spin, measuring one's spin up or down instantly determines the other's down or up. Einstein believed this was due to hidden variables, preset properties the particles carried, but Bell's experiment showed otherwise. By measuring the spin of entangled particles in random directions, quantum mechanics predicts a 50% chance of matching spins, while classical physics predicts 55%. Experiments consistently favor quantum mechanics, proving particles don't have fixed properties until measured, and that information about one particle's state reaches the other instantly, faster than light. The delayed choice quantum eraser takes this further. In this setup, a photon is sent through a beam splitter, taking one of two paths. Mirrors guide the paths to converge at another beam splitter, where the photon has a 50% chance of reaching one of two detectors. With the second beam splitter present, an interference pattern emerges, suggesting the photon travels both paths like a wave. Remove the beam splitter and the photon picks one path, behaving like a particle. The twist: scientists inserted or removed the beam splitter after the photon chose its path. Astonishingly, the photon's behavior changed retroactively. If the beam splitter was added, it acted like a wave. If removed, it acted like a particle. This implies the future decision influenced the photon's past behavior, as if information traveled backward in time. Does this mean causality is broken? Not quite. Quantum mechanics suggests particles exist in a superposition of states until measured, and entanglement allows instant correlations without violating relativity's ban on faster-than-light information transfer. The delayed choice experiment may reflect light's ability to sample all possible paths, including those influenced by future setups, without requiring literal time travel. Still, it challenges our intuitive sense of time, hinting that at the quantum level, time may not be as rigid as we perceive. These phenomena, relativistic effects, gravitational time dilation, and quantum oddities, reveal a universe far stranger than our everyday experience. Approaching the speed of light warps colors, stretches time, and distorts space, turning the cosmos into a surreal spectacle. Gravity bends time near massive objects, making a minute near a black hole equivalent to centuries elsewhere. Time, as a fourth dimension, binds space into space-time, a flexible fabric we navigate without fully seeing, and light, with its wave-particle duality and temporal tricks, defies our expectations, suggesting a reality where causality and time are more fluid than we imagine. What does this mean for us? These insights deepen our understanding of the universe's fundamental nature, from the macroscopic scale of stars and galaxies to the quantum realm of particles. They inspire questions. Can we harness quantum entanglement for faster-than-light communication? Could time dilation enable interstellar travel, where astronauts return to a future Earth? Why does time flow only forward? And what forces drive us along its axis? While we may not have all the answers, these explorations illuminate the unseen world, revealing a universe that's both beautiful and bewildering. The phenomena of time dilation and relativistic effects don't just captivate our imaginations, they hold profound implications for the future of space exploration. As humanity dreams of venturing beyond our solar system, understanding these principles becomes crucial for designing missions that could span light years. Imagine a spacecraft capable of reaching 99% the speed of light, propelled by advanced technologies like laser-driven sails or antimatter engines, concepts currently under study by organizations like NASA and private ventures like Breakthrough Starshot. For the crew aboard such a vessel, a journey to Proxima Centauri, 4.24 light-years away, might feel like a few months due to time dilation, yet upon returning, they could find Earth centuries older, with civilizations transformed or even vanished. This temporal disconnect poses not only technical challenges, but also ethical and philosophical ones. How do we prepare astronauts for a future where their loved ones and societies have aged far beyond recognition? Moreover, the visual distortions caused by the relativistic Doppler effect and aberration could complicate navigation, requiring advanced AI systems to interpret the warped cosmos in real time. These effects, while theoretical today, underscore the need for innovative engineering and a deeper grasp of relativity to make interstellar travel a reality, pushing the boundaries of what we believe is possible. Delving deeper into the quantum realm, experiments like the time slit and delayed choice quantum eraser suggest that our classical notions of time and causality may be fundamentally incomplete. If light can test paths through time, as seen in the 2023 Imperial College experiment, and if quantum entanglement allows instantaneous correlations across vast distances, we're forced to reconsider the very fabric of reality. These findings hint at a universe where time isn't a strict linear progression, but a more malleable construct, especially at the subatomic level. This opens tantalizing possibilities for future technologies. Could we one day harness quantum entanglement for instant communication across galaxies, bypassing the light speed barrier? Might we develop quantum computers that exploit these temporal anomalies to solve problems intractable by classical means? Projects like those at CERN and quantum research labs worldwide are probing these questions, building on experiments that challenge Einstein's framework. Yet these discoveries also raise profound philosophical questions. If time is fluid at the quantum level, what does this mean for free will, destiny, or the nature of existence itself? As we push the frontiers of quantum physics, we're not just uncovering the mechanics of the universe, we're redefining our place within it, inviting a new era of scientific and existential exploration.